I don't know if the sound's okay, but probably is. Right, so for the last few years, there's been a tremendous biomedical revolution happening with many technologies coming to market, many new drugs, many new inventions, ways to improve the way we do surgery. Pretty much every single area of healthcare has been transformed by technology. The problem with this is that the cost of delivering this care has been tremendous, much bigger than the current cost of inflation, for example. And something needs to change. If we are to continue receiving benefits of this kind of healthcare revolution, we really need to change the way we deliver care. We need to make it more personalized. We need to make it cheaper, and we need to make it more valuable. That's really the big picture that we're aiming for. And when we think about AI in healthcare, the way that I like to think about is that there's actually 5 pillars, even though if I put on my research hats, everyone thinks about the first one, which is improving clinical care. Clinical care obviously is the primary thing we're aiming for. We want to improve everyone's life and deliver better drugs and diagnose people better. But there's many other areas where AI has the potential to have a tremendous effect. So clinicians are not very efficient because of inefficiencies in terms of workflow, and being able to use AI to improve clinical efficiencies can have a tremendous impact, mainly around value. Auditing nowadays, we have CCG standards, we have targets that need to meet. Most hospitals would know how well they're performing maybe 6 months down the line, maybe a year down the line by looking at the data retrospectively. We can look at the data now. We can have live auditing systems running. We can check exactly the status of our hospitals now. And this way we can act and change how we are performing care so that we can make sure that we're never degrading the quality of care regardless of what's happening around us. Operational efficiency is probably the most valuable one of these 5. Hospitals are becoming these increasingly complicated factories where the things we are producing and taking care of are these things that move. They have their own opinions and they want things, right? And it becomes extremely hard to make predictions that are personalized to the point where we know how the system, how the flow hospital should react to that person being there. So managing an hospital and managing the operations of an hospital becomes extremely complicated, and it's something that we need algorithms for. And obviously, if we now put these 4 things together, what we end up with is value-based healthcare. The idea of looking at the full patient pathway from the point that the patient gets admitted with first symptoms to maybe the patient gets discharged 3-4 years down the line, completely cured or maybe managed appropriately. If we look at the costs and outcomes and value and treatments of all of the full pathway, how would we have done things differently to make sure that we can maximize outcomes and minimize costs? So there's multiple steps for us to get there. The first one is we need a harmonized healthcare record, and this is easier said than done. If you think about it, every single hospital has a different patient healthcare record, a different way to store data. And if we are to realize the idea of AI in healthcare, the first thing we need to do is make sure that all the data is stored in a way that is interchangeable, interoperable, and accessible at scale. We are achieving this with mostly 2 pieces of technology, XNAC and CogStack. Actually, CogStack is a King's product that is able to extract and harmonize data from the EHR, tag it appropriately, and action it in a way that is appropriate. After you collect all of these data, you take pieces of text, you take pieces of the EHR, you take images, you take all of this, you put them in your big box, in the big storage server inside of your trust. Now you need to make sense out of it. You need to run semantic queries. You need to be able to understand concepts of your text. You need to understand the relationships within your text that, for example, is written when you're discharging patients. The amount of information that currently exists within natural language form in hospital is immense, and really making sense out of this information has tremendous value. And because ontologies exist, ontologies are these systems where we understand concepts and relationships between them. We can then use ontologies to make very complicated queries. We could, for example, say, I want to know all my liver patients, whatever that means. And the system could, for example, use the fact that the patient is taking a specific drug, which is an NCAP agent, which acts on the liver, to then define that this patient has some form of liver disease. This search is only enabled by something like a semantic understanding of text and concepts. If we understand these concepts, we can then look into care processes. We can understand how data precedes each other. For example, here what you see is a study at KCH from some colleagues, where you look on the left side, you have a plot of different patients taking drugs for stroke management throughout the years. And on the right side, you see a similar study, but that took 10 years and involved almost 1,000 people to collect the same amount of data. This was done automatically, that was done with manual data input. And you see the patterns are very similar. with fully automated algorithms, but more than that, because we have access to the full patient history, we can also look at how they changed from one drug to another drug, why escalation was done, something that we'll never be able to do with the original data of this very large study because that was not the initial intended purpose. So automating data collection at scale enables you not only to do something you could do before with people, but actually do much more than that. Even if you look at extremely simple data, so something as simple as this, patient X has moved from place A to place B on a certain date, you can already understand hospital workflows really well. You can understand how many patients are going to arrive at a certain ward, how many patients are going to transfer from place A to place B. And the other interesting thing about it is that it's extremely predictive. If you know how your hospital looks like today and where your patients are, you can predict where they're going to be tomorrow. And you're going to figure out that maybe you don't have enough nurses in this ward. You maybe need to call them back, or maybe you need some locums. You can do massive amounts of resource allocation by understanding how patients move around in a hospital setting. You can cross multiple types of data together. For example, here is a plot of some flu-like symptoms described in patient discharge letters, so any kinds of symptoms related to coughing or something like this. And below you see outputs from lab swabs of flu viruses. And you can see that you actually see precedents. You can see that there's been this certain flu before it actually happening, just by looking at symptoms at scale. You cannot look at one report, obviously that means nothing. But if you look at everyone coming through your article, you can actually see that this is going to happen before it happens. Because obviously lab results take some time to arrive. Which means you can act by predicting these kind of unseen patterns that you didn't realize before. We also need to automate expert and expensive tasks. For example, if you're going to do quantitative analysis of images, you might want to contour some objects in images. You might want to read some images and transform them into reports. There's many tasks which are highly repetitive, and algorithms now are becoming extremely good at solving them. For example, I ran a challenge last year called the Decathlon Challenge, which the task was to solve 10 completely different medical image analysis problems, in this case contouring different objects in different images, with exactly the same algorithm. So you just have one algorithm, you need to solve the 10 tasks, and the outcome was yes, you can pretty much solve segmentation nowadays in a 100% automated fashion, with no human interaction whatsoever. And if you put all of this together, then what you get is you get this sequence of tools that go from hospital data on one side, heterogeneous data stored in these databases, you infer some structure, you'll be able to understand what that data means, and because you can understand what the data means, you can then action it, and you can then take these actions and put them back into the patient healthcare record. If you're now looking into, let's say, for example, KHP, which covers roughly 8 million patients, 4.2 million patients a year, this is a huge population covered by these three trusts. The easiest way that people think about in terms of bringing data together would be to say, let's create a big data lake. That's the classic way of doing it. And the problem with creating big data lakes is that there's this barrier there which forces you to go through this extensive governance and process of moving data and anonymizing data, which is excruciating and actually not very useful. And as part of the AI Center, what we realized was that we should be delivering infrastructure on site, on premises, at what is called at the moment AI at the edge. So we've been working with a bunch of providers, NVIDIA, Mellanox, NetApp, really deploy state-of-the-art hardware inside of the trusts. So what we can do is we have a machine learning node that can learn from data that sits inside the security lab, inside of the hospital itself, which means data doesn't need to move. And if certain subsets of data can be made fully anonymizable, then yes, we can come to King's College and we can play with the data ourselves. But more interesting than that is the primary approach that we've been following to learn across multiple healthcare systems, which is using what is called federated learning. The idea of federated learning is that when you are inside of the trust, you have your raw hospital data. This hospital data is harmonized through some harmonization layer that makes all the data look the same way. Then you insert this differential privacy gateway, which is a specific type of mathematics that allows algorithms to not be able to memorize any examples from the data, which means if the algorithms try to memorize, they can't. And then what you do is you inject this federated learning node at the firewall of the trust, so at the entry point of the trust, and you say the trust is now accepting algorithms. So you can send an algorithm to inside the trust. The algorithm can go inside the trust, can query the data, can learn from the data in a privacy-preserving way, and the algorithm can be then retrieved again and combined with algorithms that have learned from other sources of data in other hospitals. if you now combine this learning, create a consensus model, send an updated model back, learn a little bit more, come back, create a new consensus, keep doing this iteratively, you can then end up with a single algorithm that has learned from all of the different obstacles at the same time without ever moving a single bit of data and without any problems of privacy. And the last step, obviously, is if you now want to deploy this, you need to think about how do you go from a research ecosystem into a mission-critical and into a life-critical ecosystem, right? If you're doing research, if my system goes off by half an hour, I don't really care. If I'm caring for a chronic illness and I don't have the system for a few minutes, it's probably okay. But if my patient is in the bed with a stroke, and in fact now, I'm really in a life-critical situation and the system cannot fail. So we've been working quite closely with IBM to try to architecture these systems in a way that they can be made robust to achieve a specific SLA that is necessary for acute care. So really, what we would like to do with all of these ecosystems is to shift this curve, this outcomes cost curve, where we are going to introduce AI into multiple stages of the healthcare process. And by introducing AI, you can really augment the quality of care that you receive at different staging processes by shifting this curve, where you're going to improve your outcomes, hopefully for exactly the same cost or even lower costs. And by doing this is the only way, at least in my opinion, that we can really continue improving the quality of care without massive increases in costs. So just to finish, if you now have all of this ecosystem, how can you make use of it? So one of the primary things that we should be doing is, yes, we have a lot of research funding, but we need to think about commercialization. We need to think about companies coming in and making use of the data. And we just created this ecosystem where you can learn from data without jeopardizing patients' privacy. And by doing this, we have this really interesting framework where companies can come in, develop their products with obviously appropriate revenue shares and things like this in place. And by doing this, we can then create an ecosystem not only for data research in healthcare, but also for startups and for spin-outs. And in order to do this, we're actually building a new building just across the Thames from Parliament. This is something that has been announced, is the London Institute of Healthcare Engineering. And really the idea of that building is to bring in many, many different startups, either as spin-out being spun in to Kings, so companies started elsewhere, or companies that are being spun out from within Kings, and host them on that site, jointly with clinicians, jointly with academics, and hopefully by having everyone in the same place, with appropriate data access and with appropriate clinical support, we can develop products that have not been possible before. So with all of this, I would just like to say that the aim of all this is really to try to conclude this loop. Many times we get stuck at certain levels where we start with a clinical research question, we start thinking about big data, and then after that we start thinking about precision medicine and how to translate to a single subject. And we sometimes forget that if you are to reach market and have an impact, you need to go all the way to the end and really think about industrialization and commercialization of some of these technologies. And with this, I'll try to have some questions. Thank you.